All right, folks, I think we'll get started. It's just about 10 after 7. Thank you all for coming. I'm Mayor Joel Griffith, and I think you've all heard that we have the great fortune of having a letter we sent out to the wide world answered by Professor Jack Riley of RPI. And long story short, these 5 fabulous individuals have spent the entire semester working on the Tivoli Waterfront. And they're back. This is going to be the culmination and the fruit of all their hard work. And the format, we're going to let them introduce themselves, give their presentation, and then I'm going to take back over because Tivoli would like to express our gratitude to you in a special little ceremony. And then I hope we'll have a nice long Q&A because I'm sure there's going to be a lot of questions. So thank you again for coming. The floor is yours. Thank you.
Well, thank you all for having us in your lovely village. This is our 3rd time back in town. And like Joel previously said, we were here 3 weeks ago, gave a preliminary presentation to the Waterfront Committee and the Board of Trustees. We took a lot of their feedback and we're here today to talk about it.
Okay, so we just want to go around and introduce ourselves, say a little bit about ourselves. My name is Rojan Rajkonakar. I'm from Edison, New Jersey. I'm currently a senior civil engineering student at RPI, and I'll be at RPI one more year to complete my master's in structural engineering. And for the project, for the Tivoli Waterfront project, I pretty much focus on the structural analysis and some of the maintenance costs associated.
I'm Luca Degla. I'm also going to be staying at RPI for another year to complete my master's degree. I was cast as the drafter and structural engineer for this project as well. And it was a lovely experience working for this town.
Hi, my name is Sean Ozark. I am actually graduating at the conclusion of this May from RPI with my bachelor's. I'm on the hunt for jobs. The main part I played in this particular project was collecting all of the specifications that we had to sift through. I designed the staircase and I worked on a lot of the editing of the writing.
Hi everyone, I'm Casey Gardner. I'm actually from across the river in Saugerty, so the project was local for me. I'm going to have one more semester left at RPI. I'm going to finish up my master's in structural engineering. And for this project, I mostly worked on the design of the bridge piers and researching the inclined handicap lift.
My name is Patrick Arias. I also have one more semester to go. I'll be graduating my bachelor's in civil engineering. In this project, I was responsible for every geo-type related analysis of the soil and its capacity for strength with the foundation itself.
All right, so just to cover some of the major topics we're going to talk about today, we'll start with a general site overview of the proposed bridge layout. So that's basically right down the street where Diana Street, Friendship Street, and Broadway meet, I think. It's right down there. So we'll move on to discussing some of the design constraints we face with code and clearance requirements. In terms of engineering design, we'll talk about some of the bridge piers, the various roof designs, and handicap accessibility systems we went through. And we'll move on to some of the structural analysis in terms of the design loads, stresses, and member sizing. And then we'll finish up with a geotechnical summary, and we'll touch on some costs and maintenance associated with the project, and we'll finish with some future plans.
For those of you that aren't familiar with the site, this is taken from Google Maps. We're thinking of positioning the bridge just south of Diana Street here. And as you can see, the site is highly constrained by the Hudson River on the west side and then the existing property lines on the east side. With Broadway Street running parallel, there's this empty lot, so we're thinking that could be a proposed parking lot further on in the project. This is just showing the existing property lines and how close we are to them with the railroad tracks. There is a law saying that we could only be so far from the property lines. That was taken into consideration in placing the bridge. And then on the right is just an existing zoning map which shows who owns those properties and which ones the town owns.
In this particular slide, you can see our 2 original designs for the bridge. Our first thought was to create a handicap ramp to comply with ADA requirements. But as you can see on your right-hand side, that image, that's the footprint of the bridge with ramps, and it's massive. It's clunky, it's ugly. Each one of those ramps would wind up being about 300 feet long on either side. So we decided instead to, after talking with Joel, gave us the wonderful idea of the handicap lift. We decided to start exploring putting a handicap lift up along the flight of stairs on the other side, as you can see on the left hand, which is just the footprint of the bridge with a staircase instead.
So like I said before, I was the drafter, so we designed all our members from AutoCAD, took a bunch of the feedback from the last time we were in town, and this is the current working design. There's a fully covered bridge and fully covered staircase. The handicap lift that we'll be getting into later is going to be attached to the inside of the staircase. The staircase is about 10.5 feet wide. Each platform is about 10.5 feet wide as a square. The bridge has a clear width on the inside of about 8 feet. And the entire thing is 25 feet above the railway, and we'll be getting into all of that later.
One of the major requirements we had to contend with was the vertical clearance requirements. In order to have a bridge over a railway, the minimum clearance requirement is 23 feet, which increases for pedestrian bridges. So the max clearance, I think, for the bridge was 25 feet from the top of the tracks to the bottom of the bridge. In addition, we had to deal with horizontal clearances, so the slope in the area might require some cut, which means we'll have to remove soil from that particular area. And on the east bank, and fill, which means we'll have to take that cut out soil and, I guess, fill it in to smooth out the slope on the west side of the bank. More geological data is really needed for that, though. We don't have the resources for the soil surveys. The bridge materials that we're mainly using are steel and timber. Steel for its structural capacity, and timber because it's just way more aesthetically pleasing. We wanted to make sure that we were presenting to you guys a bridge that wasn't an eyesore on the community.
For the structural system of the bridge, we had initially gone through just Googling images of bridges we thought that the town and Tivoli would like. Our first design was a bird truss, which is in the lower right-hand corner. But when we started to do some analysis of it, we realized that that truss had excess capacity, which means it would have been better suited for a larger span bridge than what we needed. So then we looked at the individual components of that truss, which would be an arch and a Pratt truss. In the end, an arch would have been more difficult to construct to get that curvature right, and it would also have taken up more of the view shed. So we had our design is a Pratt truss, which is efficient to design, efficient to build, and it stays with the aesthetic of like the old railroad bridges. The bridge piers, after consulting with the village of Tivoli at our last meeting, we had gone with a steel tower design. This is an example one in this picture. The photos on the right are structural analysis of it, but it's a 3D steel tower with cross bracing. It's comprised of two sections, an HSS member, which is this hollow steel tube, and then angles for the cross bracing, and this is all made out of steel. The piers were analyzed in a computer analysis program and checked for all the loading, and then the member sizes were optimized accordingly. For the alternatives, we had looked at concrete piers and then also timber piers. We liked timber because it would go with the aesthetic of the bridge. However, in order to get the capacity we would need, the timber piers would be massive. So having steel piers allowed us to have a smaller footprint and a smaller column thickness. And then concrete is very good for taking compression, so we could take a lot of load with that. However, they're not as very aesthetically pleasing. So one of our earlier design was with a concrete column, but when we consulted with the village, we realized that the steel tower piers were more pleasing to everyone.
So for the time being, this is the primary roof design. There are a few alternatives that will follow, but this is the cleanest design we found. It's all orthogonal with the bridge. It's neat. It takes up less of the view shed. There are a few code requirements that say that we have to drain water away from the train track by law, and there are certain code requirements that say how much an angle has to occur on the roof or the deck, how much water needs to be flowing away from the railway, specifically. But as you can see on this slide, you can have a lot of play with it. I drew up a few options in AutoCAD just to show that you have a lot of free play with this should the town go further with the project, as long as the engineers on record, because we can't be the engineers of record, we aren't licensed, but as long as they follow those code requirements, you can have a lot of fun with it. Then there's the stair design. The stair design also has certain code requirements. You have to have landings of a certain size every so often. And last time we were here, we decided to go for a covered stairway because it helped keep water and snow and ice off the stairs. And we also made the staircase wide so we could put the handicap lift and ramp just on it on the inside, and we'll be getting into that soon. More stair design, I went through the exact measurements earlier on. Just, it gives you a little bit more scale and perspective of how big this bridge will be. We'll have some renderings later. Now there's the stairway columns. In order to support the stairs, we felt that classically cast iron was preferred. It has, I don't know if anyone's been to the Harlem 125th Street train station, but you have those really nice cast iron columns that support the roof. And I figured something like that could be done. It's a little bit outside of the scope of what we've done in school, outside of our design experience. But once the loads are given to a structural engineer, those loads will be transferred to some manufacturer for cast iron columns, and the manufacturer for the iron will come up with the exact size of the members that would be needed.
For the ramp, this was our initial design before we switched over to the stairway design. As you can see, the footprints for either ramp were massive, just ugly and massive and unappealing. So that's why, after speaking with Joel, we decided to move on to onto the stairway, which was way lighter and way more visually appealing.
We had initially heard from Joel that someone had mentioned the incline lift at the Roosevelt Library, I believe. So we started pursuing that as an option. Doing some initial background research, we found that this is also a pedestrian bridge over a railroad track. This is in Montana, so we kind of use that as our inspiration. They have more of like a gondola style, but further research in it found this GSL Artera incline platform lift, which is primarily used in outdoor sporting arenas. And this platform lift is ADA compliant, and it rides up the actual staircase on a set of guide rails integrated with the railing, and allows handicapped people to ascend the staircase. These are just some specifications of it. This is off to the side when it's not in use, and then you can kind of see this steel tube that it rides on. And the largest platform size is ADA compliant. It is available for outdoor applications, which is what we would need. It has a maximum travel speed of 20 feet per minute, and then it slows down right before it begins and ends, and then when it encounters a turn. And then it also has built-in safety features. It can sense if someone's on the staircase, so it will stop. There's flashing lights to alert people. And then there's also the sides flip up so that the wheelchairs can't roll out. To power this thing, we would need a 2 horsepower electric motor. And then that's just some information on the power requirements. None of us are electrical engineers, but I've been assured that it would be very easy to power this thing, and if we don't want to connect it to the grid, we could possibly even look into solar panels to power the lift.
So we were given the task of figuring out how to get a kayak up either to the bridge itself and then down, or figure out how to just get a kayak across the entire structure. This is a very crude sketch to prove the concept that we came up with, specifically Patrick and I. Basically, you would take these 2 rail systems that would run parallel to each other on the outside of the bridge, and at a certain point, they would get further away. So you would take some kind of spring-loaded hook mechanism strapped to the inside of the seat of the kayak on a horizontal position, and as it went up through either some kind of hand crank or probably a motorized form of transportation, it would be drawn to the vertical position based off this separation in the railings. Then they would come back together later on the bridge, and you could just get it back into the horizontal position and just take it back off the same way you loaded it on.
Okay, so moving on to some of the structural analysis. Before we can get started with analysis, we have to obtain some design loads to load the structure with. So here we tabulated some of the major gravity and lateral loads, and we referenced some of the national design guides such as ACE7 and the AASHTO Pedestrian Bridge Design Guide. And just most of these are self-explanatory, but just to explain a couple, the dead load represents the self-weight of the structure, so the bridge itself, all of its components, its structural components. And the live load would represent like pedestrians or users of the bridge. So these are just to summarize some of those loads that we use. So with the loads, we decided on a truss structural system for its efficiency to carry loads and limit deflections. So on the left, you can see the set of gravity load trusses, which we designed to withstand those dead loads, live loads, and snow loads. And we combined that with a lateral load truss system down at the roof level and below the deck. Those would primarily resist the wind load and earthquake loads. So just like kind of an image, this is our structural analysis program. This is the image you'd see when you put those two systems together. Okay, so member sizing. After we went through and we loaded the structure, we wanted to size those members and make sure that none of them were overstressed. So this is basically just, on the left is the gravity load truss member sizes, and on the right are the lateral load truss member sizes. And in the red you can see the steel members, and in the green are the timber or paralleling members. And I basically just wanted to put these on here to show you, all these numbers represent dimensions in inches. So just to give you like a gauge or a perspective of how big these pieces would be. The biggest pieces would be the truss cords. You can see the top and bottom cords of each of these trusses are, as Casey mentioned earlier, an HSS, which is a hollow structural shape. And it's pretty much just like a tube of steel, 10 inches wide, 10 inches tall, and a half-inch thick. So those are the member sizes. Moving on, our structural analysis program is called SAP 2000. Here are a couple shots of the whole structure as we loaded it with those gravity loads and the wind loads. And pretty much, it's hard to see a little bit, but the colors represent the amount of stress in those members. As you can see, most of it is blue, which represents a lower stress, somewhere between 0 and 50%. And we tried to avoid any red members, which would represent an overstress. And we were able to do so effectively. And by code, we were limited to a deflection limit of L over 360. So L standing for the length of the bridge, which we designed an 80-foot bridge. So if you take 80 feet and multiply by 12 and divide by 360, you get 2.67 inches, which was the maximum deflection we were allowed. So after running it through the program and sizing the members, we were able to keep the deflection in both directions, gravity and lateral, below an inch. So that's well below our allowable 2.67 inches. And then I tabulated basically the maximum stresses that we found in each of the members. And just to give you a gauge, those top and bottom cords we were talking about before, they have to withstand a max compression or tension of 50 kips, or basically 50,000 pounds of force.
For another one of our major concerns was detailing. We didn't really design for detailing, but we definitely thought of a lot of different detailing options. For example, driftwood railings would be an option. We all believe that such a thing would be more aesthetically pleasing on the bridge, as long as a copper-plated caging, because as stated previously, the entire bridge has to be enclosed, so pedestrians can't throw debris onto the railway tracks, so no one falls off and jumps onto the railway tracks. It all needs to be covered. So we were thinking about copper plating for the mesh that would go over the bridge, because you would have that nice oxidation over time. Another thing was we need to put bollards, which are those giant concrete, they're giant and yellow and concrete that keep your car from going somewhere, on the tops of bridges, because as I was told by someone who works in my engineering office, where there's a will, there's a way. So if someone can get it, if someone has a golf cart and thinks it's a great idea to try and drive over the pedestrian bridge, chances are someone at some point in time will try and do it. So we were thinking about driftwood or wooden bollards to put at the top of it, just to make the entire thing more aesthetically pleasing.
I'll talk a little bit about the sheet piles. Sheet piles are walls made of concrete or steel or wood. These walls serve for vertical, horizontal loading of the soil while you excavate. For when you do excavation, first thing you do is perform the sheet pile, so then you just continue going with your excavation. There's the River Hudson was kind of complicated to build this foundation for this bridge. According to the degree that you'll face here on the soil, that will highly difficult, like make it difficult for building a foundation itself. They would require like more study of how deep will it go and how fast will it go, so that you could easily discover the degree for it and have an even better calculation for its capacity. So we ended up choosing a spread footing, basically because the soil like underneath 17 feet is a very weak soil for pile foundation. So to begin with the excavation, you can see here in the back, this is the sheet wall that we would have to build. It would have to go 28 feet below, and we'll start building the foundation at 12 feet below. This is a cost analysis of removing the soil and recompacting it on the place. Also with the pile sheet also included. Pile sheet is very expensive in this case. You can easily see it's overcoming everything for that, but it's essential for doing this type of excavation. The location of the footing will be located at 60 feet north from Diana Street. You can see here Diana Street would be around here. Yeah.
Okay, so moving on to the cost estimate. We're still currently compiling like a comprehensive cost estimate, which we'll include in the final report. However, to begin, we began with like an estimate for the truss. We contacted a company called Excel Bridge, and we asked them how much approximately it would cost to design or fabricate a bridge with the approximate dimensions similar to ours, 80 feet long, 8 feet wide, and they came back with $66,000 pre-tax for the town of Tivoli, and that would include the fabrication of and delivery of a Pratt truss bridge made of weathering steel, as you can see in the photo here.
For the bridge piers, the way structural steel works is it's typically bid on by contractors as a lump sum pricing. So where this number came from is I went to a steel manufacturer's website and put in the sections we would need and got a price for that. That does not include like labor or putting it together, connections, anything like that. That's just a rough estimate of the material cost. We would likely be able to get this made by a steel manufacturer and have it come pre-assembled to the site. And then for the inclined handicap lift, I'm currently in talks with them. I had emailed them a while back and they finally got back to me. So they have our plans for the bridge, all our dimensions, all of our drawings. So I expect them to get a number back to me, hopefully within a couple of days, and I'll forward that on to you guys as soon as I have it.
Like I mentioned before, basically with the soil-related estimation is just removing the soil and refill it, compacting it so that it could withstand the capacity of the bridge. You will also locate here for the concrete footing, the estimation, and like I said before, the thing that is most costly is the pile sheet that would have to go to a length of 60 to 50 feet around, because you would have to excavate and do a ramp to put the footing for the bridge and footing for the stairway.
So we just want to talk a little bit about maintenance as well. I guess you could relate maintaining a bridge, it's like very similar to maintaining your cars. You want to set up a schedule, so like your car's every 3, 4, 5,000 miles you get an oil change. You could say something similar for a bridge, just maintaining the various structural components and the deck and whatnot. So we basically put together a table here. It's just some of the major categories. There's going to be a lot more. Like I said, we're compiling like a table for the final report. But just to talk about a few, just repainting the steel and timber. The reason those came out higher was because those are your main structural components. You want to keep those in good shape, keep those strong, keep your bridge strong. The snow and ice removal, those costs could add up as well from year to year. But I guess a way to maybe avoid that would be you have the option to close the bridge maybe during the winter months if you don't use it very much, and that way you could you could keep it safer and avoid accidents like slipping on the ice, and reduce some of those costs from clearing it. And the deck repair and replacement, if we were to design the bridge with a concrete deck, that number would have shot up probably higher than even these two at the top here. But we chose a wood deck system to keep those costs lower.
When we were here previously, we had heard that, or talk of a possible observation platform overlooking the Hudson. And while we really wanted to design this for you, we would need to be able to have access to geological soil data that we just don't have the ability to go out and test for. You know, I couldn't tell you what the soil is like under the water on the Hudson, and unfortunately it'd be we'd have to get an engineering company to get that data for us. But it's definitely a very feasible engineering option that, moving on from the future, if you wanted to design for, you most certainly could. But we just don't have the resources at this time to be able to properly design that for you in the way we would like to. Our plans for future work, or our suggestions to you, since this is pretty much the conclusion of our project, would be to get soil studies for the area, the surrounding data, because our access to this information was really very limited, and that's very typical for areas. Technically, you only get in-depth soil data done by engineers for specific building sites. Look into solar panels possibly for placing on the roof, so you don't have to deal with the additional electricity costs or running the handicap lift, and bringing this to an actual engineering firm, because once again, we're not licensed engineers, and
Soon.
so at this time, we'd love it if you guys had any questions for us.
So, and I want you to hold those questions in your mind, because I'm going to distract you with a really nice ceremony now. We had said this in our letter a long time ago. I don't know if you remember it, but we're about to offer you the distinct honor of becoming honorary Tivolians. We've had these certificates. I'll read it to you. There's one for each of you. Let it be known that in recognition of the time, intelligence, and imagination generously donated to the village of Tivoli, New York, culminating in the design of a pedestrian bridge for our future waterfront park, the people of Tivoli, here they are, wish to honor such invaluable service to our community by naming you an honorary Tivolian. Please accept this honor with our profound and perpetual gratitude. So, we have one for Lucas. And of course, this wouldn't have happened without Jack. Your wording is a little different because they did all the work on this. Let it be known that for his dedication to the education of his students, his commitment to challenging the engineers of tomorrow, and for answering the earnest call of a small village with big dreams, the people of the village of Tivoli, New York, hereby name Jack M. Riley, an honorary Tivolian. Please accept this honor with our profound and perpetual gratitude.
Oh, thanks so much.
The honors aren't over. I have here on my lapel one of the rare and coveted Tivoli, New York lapel pins. Now hopefully these certificates will be in your offices at the firms that you'll be running in the future. But I know you like to go out in the field. I recall the photograph in the snow of you with the tape measures and stuff. So to remember us even when you're out of the office, we have some Tivoli, New York lapel pins.
Show the man what he's won, Johnny.
Yeah.
Thanks so much, Johnny.
All right. Thanks again to all of you. It's really been wonderful.
Thank you.
You want to raise your hands and kind of moderate? And, any questions for our engineers? Yes, Jeff.
An amazing job on the project overall. Very impressive. Could you show on that picture there where you can imagine that structure for the kayaks, for example?
So this is a somewhat outdated rendering. The architect we gave it to was basing it off of an old file. It would be running on the outside of the staircase and on the exterior of the bridge. So you could have two systems that run parallel to each other on each side of the bridge, one on our right and one on our left. Both of them would wrap around the entirety of the bridge, and you could have two people sending kayaks in opposite directions.
And this is 60 feet south of Diana, because someone was saying 60 feet north. So can you?
Yeah, this is
This one's
south.
south.
Yeah, if it was said that it was north, we most certainly mean south. All the bridge plans have been done for south of Diana.
Just out of curiosity, at the beginning, you very, very quickly made a point about deciding where to actually place the bridge, sort of the north end of the parcel versus the south end, and you chose the south, so the entire presentation has been around that. I'm curious what led you to choose the south versus the north, or the middle, or any other spot, and if you can elaborate on the pros and cons either way. I guess I just feel I want a little bit more information about that decision.
Can you go back to the site overview?
Let's start with the plans, right? In class.
I think, yeah, it all started with the plans in class when we were looking at the allowable space for the property lines. It's very, very spatially constrained, especially when you start to think about the areas owned by the railroad. I highly doubt that you guys want to have to go through trying to buy property from the railroad. I think we were talking to Joel about that earlier.
Yeah, we already did.
It was a pain in the butt, I
Yes.
think. Yeah. So that was the initial part of it, was not wanting to encroach on anyone's land or the railway's land. Unfortunately, we were looking at a bit of an outdated existing property line scheme. So everything that we might have based our property line information off of may actually be incorrect as of today, just because we were working off of an old, was it from the early 2000s?
2004.
Yeah, it was from 2004. So that was part of our consideration. The next part was we actually went out here in the middle of winter and we, hiked through and we measured out how much space what our actual clearance would be on either side of the train tracks, without interfering with what looked like a staging area for the railway. You have a service road and it looks like a staging area for being able to do work. We didn't want to encroach on the area because we assumed that it was in use by the railway. We're not really sure what
We're not really sure what the land rights dictate.
with the land rights that were. So we wanted to establish a site that we knew we had the available land and property allowances with. We didn't want to have to make you guys battle it out with the railroads again.
So if you were to have a parking area up in the north part of the section of the lot, you would have to still transport the kayaks, for example, all the way down to the south part? Or would there be a way to sort of drop them off maybe before going up to the parking lot?
I mean, you could probably even just ditch them off at Diana Street,
Yeah.
because this bridge, the way we have it designed at the current moment, you can access it, I guess, north to south, so going southways when you're entering the bridge and getting off the bridge, it heads north. There was some talk about making it symmetric on either side, so both stairways pointing north or both stairways pointing south, but with spatial allowances, it didn't really, we assumed that the plans that we have state that you guys were planning on making this park around this area here, which is why we focused on being able to access that area. So we figured you could drop a kayak off on Diana Street, put it on the bridge, and then if you wanted, you could go park your car. But the main purpose of it was to be able to access that park as well. I guess two main reasons. Does that summarize everything right, guys?
Mark?
But just to stick with this, I mean, this design flexible enough that, given the right soil conditions, you could move it anywhere or
Yes.
change the orientation of the
It might even
staircases.
be easier if we have certain soil data, because we might be able to do a pile foundation if you had certain, if you had certain soil data and you
Well,
moved it.
the soil data that I received, the boring log is like where they excavate and take a sample of the soil. They didn't tell me precisely where they were inputted. So all my calculations were based on a weaker soil, but it could have been a stronger soil also. For the cost of excavation and sheet piles, to minimize and get those out of the way, we could do pile foundation. But for pile foundation, we would have to have an increasing study of your rock bedded, that soil withering shale that is very weak. Normally this is only acquaintance with like a local experience or with further study of the soil. Since I don't possess none of those, I went with the more secure option, that would be the spread footing itself.
But a pile foundation could significantly reduce the cost of the
Yes.
bridge altogether.
Yes.
Pile foundations are very cheap.
With that pile foundation, I'm sorry, I'm not covering your line. With the pile foundation, did you still need that shield wall or whatever it's called?
No, you would not. It's pile foundations. It's quite easy in this case. You do just this. Can you put on the footing itself real quick? All right. So imagine that footing over there, that square footing, going all the way up to the surface. Pile foundation is simply putting all these concrete piles all the way down, and those are the ones that are gonna sustain the heavy loading.
And those can either be driven in or vibrated in. They don't have to, you don't have to excavate anything.
Yeah, you don't have to excavate nothing, it just drives in. Normally it's more expensive than spread footing, but because of the sheet piles they're huge sheet piles, they're 28 feet.
Yeah.
And also to perform these sheet piles, we needed to perform the sheet piles because the railroad crosses here and we can't stop railroad, it has to continue. So that's why it's necessity of this sheet pile.
Do you have any more questions?
The roof design over the tracks,
Yes.
is that gonna dump snow on the tracks in the wintertime, or where's it gonna go?
So in this roof design, it's a little small in this drawing, but on the left-hand side, there are two troughs that act as gutters to catch rain, snowfall that falls from the roof that would otherwise fall into the tracks. The exact size of those would most likely involve a further study, involve local experience with how much snowfall is typical. But besides that, the entire point of the code is to minimize the impact of rain and snow that would otherwise fall into the tracks.
Nothing is directly draining onto tracks.
Yes?
Is there one particular roof design that would support solar panels placed on the roof over another design?
That becomes a matter of local codes. I know for a fact that in the Albany region, depending on how the solar panels are mounted on the roof, they have to be at certain angles, and those angles can't change, they're a fixed angle. I want to say it's somewhere in the 20-degree region. So if you had maybe something that wasn't necessarily peaked in the middle of the bridge, but same general longitudinal design, but maybe a little taller peak longitudinally, then it might be able to support the angle, and you would be able to mount the solar panels directly onto the roof.
I was thinking to worry about if you have a drainage troughs on the top, you won't really be able to have, that's what these are. In the original drawing, you had the drainage trough on the bottom. Up here, these little lips serve as the drainage trough for the snow and ice and water. So I think that might get in the way of these solar panels as well. That could potentially impact that.
Yes, sir.
I understand that the railroad has a 30-foot easement on both sides of the track. How do you avoid, or how do you get permission to build your stairway or ramp on that 30 feet easement?
We don't even come
Yeah.
close to it, or we.
Yeah, I was down there with some gentlemen from Amtrak last week, because of course they are now leasing from CSX, so we have yet another player in the picture. And we were looking at some maps, I believe it's 25 feet from the center of each track, and the ends of the bridge are outside that entirely, so we're obligated to keep the right-of-way for the railroad.
If you go up one. You can also see the clearances for the elevator tracks here, so it winds up being around 25 feet on the other side, maybe less. Yeah. And since this clear span of our bridge is 80 feet, so it's, from pier to pier is 80 feet, it doesn't even if it was 30-foot easements, we would still have about an additional 10 feet on either side that allows for that horizontal clearance.
It should be noted, though, in the cost estimate that we gave, it wasn't fully comprehensive, because in order to construct a pedestrian bridge over a railway, flaggers will have to be hired about $1,000 a day for 2 of them. There will be a lot of maintenance that has to occur during the actual construction so that the railway can continue to function.
I'd like to put the same question to you I put to you last time, which is, I guess it's coming from a place of guilt, which is Tivoli's getting a lot out of this, and we're so pleased and grateful, and I just wanted to ask, again, what you've gotten out of it, and I don't know if your answer may have changed since 3 weeks ago, but...
I've definitely learned a lot about pedestrian bridge design. I could see myself working on bridge design in the future as a result of this project.
is it different to be out of the classroom and be working with a...
Definitely. We've got
Real
an
physical
invaluable
site, yeah.
experience compared to other groups who are designing a theoretical project on a theoretical site.
We haven't even started yelling at you yet.
Don't make us cry, we're just students. We're already broke.
Any other questions?
Is it the kayak travels internally?
The kayak would travel external
It's
to
on the outside.
Yes.
What prevents one from falling off on a train?
We're not mechanical engineers, so we can't design the exact system. But what I would imagine or foresee is some kind of spring-loaded clamping system that would go on the inside of the kayak. And might have 3-dimensional control, 3-dimensional hold, so it has full, complete hold over it.
Any idea how long it takes to travel across it?
It depends on the strength of the motor.
Is that kayak, canoe, and any type of
I-
windsurfing and all those?
It will
forms?
depend, I think it will depend on how you, your system of locking. Initially, we had a hook system, and it would be flexible to extend and open according to the size of the kayak. But like I said, it all depends on the mechanical engineering and how they design this hook that would hold the material. If you would ask them to, all right, we want to require for something that we could put like a windsurf board or a kayak or etc., and they would design for that in that case.
Was this a trade-off that, I'm sorry, was this a trade-off that we made to put the roof over the stairs, that we could no longer put the kayaks on the lift itself?
It's not so much that. It was brought to our attention last time after we presented that certain people in the community might not have the strength to carry the kayak all the way up to the bridge level and carry it across. There should be plenty of space. We designed with it in mind to maneuver a kayak up to 16 feet within the space of the bridge, should someone want to,
Just lift it up and
And the kayak winch lift, that's not something you can buy in a store.
No,
That's
it would have
something
to
you're
be-
designing, we sort of suggested. What we need is this thing that doesn't exist, can you come up with this also?
Yes.
Yeah, we have this
Right.
theoretical idea, and none of it, I don't think, is actually, we don't have any design specs for it, we don't have
Yeah.
we just kind of
Right.
these two boys came up with with a theoretical idea of how it would work, so we don't have any specs for you or how it would actually work.
Any structural engineering firm that this project was brought to would probably have connections to a mechanical engineer that would be able to design this fully. so that would be something to consider.
Be sure and get the patent on it.
Just put a rolling
Well, you could put a chain right down the middle of the roof line, so you just hook the kayak to the thing.
Yeah, you could do it on the roof.
This is probably more for you than them.
All right.
I'm looking at this site. I'm assuming that the village will also have to construct a fence along the tracks?
Yeah, I mean, basically when this bridge goes in, as soon as construction begins, all the frontage of the parcel that we own would have a fence. And then the understanding is that there would still be an at-grade crossing, but it would be an emergency. It would be basically closed for all intents and purposes. There's no crossing. If someone was in our park on the west side and had an accident, then an ambulance could get across to service them. But otherwise, it's basically, there's no other way across except up and over.
Would you be fencing on both sides?
Basically,
Of the
yeah.
track?
Yep, you know, we have 2 parcels, and they would be entirely fenced where they face the road. Anyone else? Okay, well, thanks again. Thanks so much.